Bismillahirrahmanirrahim. Inshallah, let's continue with our chapter 6, bonding of atoms. In other words, how atoms combine with each other and produce chemical bonds. There are many different types of bonds, but the three most basic, most fundamental types of bonds are ionic bonds, polar covalent bond, and covalent bond. And even more simplistically, you can say bonds are of two types. There are covalent and there are ionic bonds. Okay, and in terms of covalent bonds, there are two. There are polar covalent and non-polar covalent, and here's an example of an ionic bond. The basic differences in ionic bonds, okay, electrons are transferred. So this atom has given its electrons in its entirety and for good to this atom. Whereas in covalent bonds, electrons are shared between two atoms, okay? So in ionic bonds, electrons are transferred and given up and taken over, so to speak. And in polar bonds, they are shared. If they are shared equally, that's called a non-polar covalent bond. If they are shared unequally, that means this atom has more of that electrons than the other one. It sees more of the electron than this one. That's called a polar covalent. So if the electrons are shared equally, that's a non-polar covalent, and if the electrons are shared unequally, that's a polar covalent bond. In terms of studying these, we're going to study the ionic bonds first, inshallah. An atom in its natural state is neutral. It does not have a positive charge and it does not have a negative charge. That is because the number of protons equals the number of electrons that are in the atom. So a helium atom, a hydrogen atom, lithium atom in its natural state, right, is electrically neutral. It is electrically neutral. If you recall, there are four forces: gravitational, electromagnetic force, okay, and strong and weak nuclear forces. So a neutral atom is electrically, a natural atom is electrically neutral. If the atom, for example, were to lose one of its electrons for whatever reason, see, electrons are easy to lose. You know, if you rub your hand, you get a little static electricity. That's because those electrons are being rubbed off. So electrons are easy to lose and gain sometimes. So if an atom loses an electron, so here's the atom, for example, here's an electron, and the electron goes away from the atom, then the electron will be less negative, right? So one of the electrons gone, so it will be positive, but because it will have more protons than it will have electrons, so it will be a positively charged entity. If an atom, for example, gains an electron, so here's an atom, okay, and here's an electron, and it comes over there and makes this atom its new home, so this atom will have an extra electrons than it does in its natural state. Then it will have a net negative charge, right? Has gained an electron. So a neutral atom, when it loses an electron, becomes positive in charge because the electron's gone. That negative, electron doesn't go without it's taking its charge with it, right? So electron leaves and takes its negative charge with it, so the atom becomes positive. When an atom becomes positive, it's no longer called an atom per se. It's called a cation. When an atom loses or gains an electron, loses or gains an electron, it's no longer called an atom. It's called an ion. Okay. So these are both ions. A positive ion is called a cation. A negative ion is called an anion. Positive ion is called a cation. A negative ion is called an anion. That's pretty easy to remember, even from my high school days. I remember this. How do I remember cations from anions? Well, cations are positive. Cats have paws. See it, paws. Positive. So cations have positive charge, anions have negative charge. Okay, this is a good one. I lost an electron. Are you positive? Ha ha ha. So cations are positively charged atoms, and anions are negatively charged atoms. Okay, so we got that. Okay, so now, if you recall, atoms want nothing more than to have a completely full valence shell, right? It's like they're envious of noble gases. They all want to be like noble gases, right? So fluorine, for example, has 7 electrons in the valence shell. It wants to have one more. Okay, let's say somehow fluorine gets an electron and fills over there. Now fluorine has a completely full valence shell. It's happy, right? You say it's happy, right? Yeah, happy. So now however, it's a fluorine ion. It's a fluoride ion. It's a negatively charged. It has one negative charge because it has one extra electron. Okay? So when fluorine gets the electron, completes the full shell, the shell is happy because it's more stable, but now it has a negatively charged, but it has negative charge. Now look at sodium here again, if you saw before. Sodium has 1 electron in its valence shell. Now, as we said before, it's going to be tough for the sodium atom to get 7 electrons. Who's going to give it 7 electrons? Good luck, right? But it's going to be easy for it to lose the electrons. So when sodium loses its electrons, this electron goes away somewhere, then it's going to have 2 valence shells that are full, that are completely full. So it's going to be happy, right? Right? It's going to be happy, except this has a positive charge. Okay? So its valence shell is fine, but now it's not electrically neutral. Here it was electrically neutral because the number of protons equals the number of electrons. Here the valence shell is full, but now its protons is greater than electrons. So it lost its electrical neutrality even though it filled its shell. So an atom wants 2 things. One, okay, it wants a electrical neutrality, right? It wants protons to be equal to electrons, right? Okay, it wants ideally, and it wants electrical neutrality, and it wants a valence shell to be full. So this is what drives chemical reactions. So you must understand this, okay? So atom wants electrical neutrality, so like this, but then it also wants its shells to be full. It's like you can't have both, right? You can have your cake and eat it too, type of thing. But okay, fine. Now look what happens here. Sodium atom, same phenomenon. Sodium, it loses its electrons, but then it gives it to chlorine because chlorine wants an electron. Chlorine really wants. It's got 7 right over here. It is more than happy to take. So, but sodium loses the electron, becomes an ion, a positive ion, sodium ion. And when chlorine gains an electron, it becomes not an atom anymore. It becomes a chloride ion. So now you have a positively charged sodium and a negatively charged chloride. So they're both happy in the sense that the valence shell is full, that is, this is met, but there's no electrical neutrality. But if they get together, between the 2 of them, they will have electrical neutrality because this is positive 1 charge and this is negative 1 charge. So it's like one big happy atom in a way. They're 2 atoms, but one big happy atom. Do you follow what I'm saying? The valence shell will be full and they will be electrically neutral if they just hang out together, and that's what they do. They form sodium chloride, which is table salt, which you would put in your food. Okay? Table salt, right? So that's what happens. So sodium, okay, loses its this is sodium fluoride. This is in toothpaste. Sodium loses electrons to fluorine, and that becomes a negative, and then they hang out together to maintain electrical neutrality, right? Check this out. Now they're ions and positive, and they hang out together to maintain. So once they do that, they will have both completely full valence shell, and between the 2 of them, they will have electrical neutrality. They've met both of their life dream goals. Now this is another representation. Now look what happens here. Instant replay. Sodium and chloride. See, sodium is going to lose that electron, give it to chlorine. Completely give it. This is an ionic bond, right? Completely give it, and they hang together because one is positively charged and one is negatively charged. They're not sharing electrons, giving away. Now this is another representation of the same thing. Sodium is going to give away the electron, and they're going to hang out together and form an ionic bond. Now I like this one because this one shows something else. See, when the sodium loses its electrons, it becomes smaller in size. The atom size decreases. See? That's important. Yeah, the atom size decreases. That's why, see, many times the atoms depicted are smaller like this, because it became smaller because it gave the electron to the other one. Okay, so that's ionic bond. Ionic bonds is where electrons are completely given by one atom and taken. The covalent bonds, as I said, are sharing of electrons. Equal sharing is non-polar, and unequal sharing is polar covalent bond. So here's an example of hydrogen. Each hydrogen atom has one electron. It wants two in the orbital, right? The first orbital. If they combine together and they share the electrons, that's called a covalent bond. Just like over here in this picture, they form a covalent bond. We love the people who made this thing. All right, watch again. So they're sharing an electron. Obviously, the electrons are going to sit right there. They're going to like do more of this. They're going to go all over the place like that. But this is a covalent bond. And the sharing is going to be equal because they're the same atom. So this is an example of a non-polar covalent bond. So covalent bond is when there is sharing of electrons. So here's hydrogen atom come together and they share the electrons because between the two of them, their orbitals are full. And ionic bonds is when electrons are transferred from one atom to another atom. So covalent bond and ionic bond. This also occurs in water. So water, as you know, okay, is this. So hydrogen atom wants to have two electrons. It really wants one more in its shell. Here's two hydrogen. And oxygen needs two more. So it needs one over here and one over here to complete 8 electrons in its outer shell. So what does it do? Well, it shares this one over here and shares this one over here, and it shares its electrons. So now between two hydrogens, oxygen has 8 electrons. It's happy, right? And the hydrogen has 2 electrons, and it's happy. And this is H2O, or water. Okay, so this is a covalent bond because they're sharing electrons. Electrons are not transferred to the oxygen. Okay. But, okay, it's a little bit more trickier than that, all right? Okay, so what happens is, okay, so here's oxygen, okay? So here's oxygen, okay? And these are 2 hydrogen atoms. Okay? So what happens, however, is even though the electrons are shared, the oxygen atoms has a greater share of the electrons. So if I were to draw an oxygen here and hydrogen over here, and this was the electron, even though they're sharing, majority of the time the electron gets to be with the oxygen, and occasionally drifts off over there. And same thing over here. Majority of the times it stays with the oxygen, and occasionally it drifts off to the hydrogen atom. So there's unequal sharing because that oxygen atom, which is a much bigger atom, has greater affinity for that electron. So there's unequal sharing. Okay, so electron spends most of the time in the oxygen, almost as if it's got the electron by itself. So because it spends most of the time with the oxygen, it requires a slightly negative charge. Electrons are negatives, okay? So it gets a negative charge. We call that delta negative. Delta means is a Greek letter. That's a lowercase Greek letter delta. This is capital delta. It's a lowercase delta. That's D. It's like D and little d. That's in Greek letter. So that's a lowercase delta. So it requires a slightly negative charge, which means that it is slightly negative on that side. And because the hydrogen is kind of not getting enough of the electron, it's kind of like slightly positive. Not completely positive, but slightly positive. We call it delta positive. Okay, so and that's what we mean by polar covalent bond. Okay, it's unequal sharing. In the polar covalent bond, oxygen is slightly negative over here, and hydrogen is over here. All right, slightly positive, delta positive, because the electron is spending so much time with the oxygen. Now, if you recall, atom's dream come true is like really 2 things. One, it wants electrical neutrality. Okay, it wants all the positive equals to negative. Okay, and then the second thing that it wanted was to have the complete shells, complete orbitals. So it wants the orbitals to be full, right? It's okay. Now in this case, the orbitals are full, but there's electrical neutrality is there, kinda, right? It kinda there, but it's not completely there, right? So what are we gonna do? It's like, oh, oxygen goes, man, it's not the best deal, and hydrogen goes, man, it's not the best deal. But wait, there's more to the story, okay? So this is an example of a polar covalent bond, okay? But now look what happens though, okay? Here's I'm going to try to draw another water molecule. See? Okay, and then I'm going to draw another water molecule over here. This looks pretty good. And then let's just do over here one over here. Okay. All right, but now look. Water molecules are not by themselves, they're usually surrounded by other water molecules. So here's, I do a couple more water molecules. Now this is oxygen in the other water, it's slightly delta negative because it's got that electron going about, right? So there's another one over here, it's slightly delta negative over here, right? And then here's the water, which the hydrogen atom, and it's slightly delta positive over there, and this is slightly delta positive over here. But now see, atoms are smart. What they do is, okay, so, well, I'm slightly negative. Hey, anybody around that's got slightly positive that can like hug me and, help me out here? So that's what they do. So there's an attraction between this slightly positive over here to the slightly negative part to balance the charge, to balance to get electrical neutrality. And same thing here, the positive on the hydrogen over here with this oxygen here. Okay, so and this over here, okay, the interaction between two different water molecules to achieve this electrical neutrality, that's called hydrogen bonding. Hydrogen bond. So that's a hydrogen bond. There's one over here and there's one over here. That's an attraction between the delta negative oxygen and the delta positive hydrogen over here, and an attraction between the delta positive hydrogen and the delta negative oxygen to achieve that electrical neutrality. Once they do that, if you were to draw another water molecule over here to make everybody happy over here, right? Look at this. Let's do it right here. Oopsie daisy. I didn't mean to do that over there. Well, let's just kind of like for completeness sake, okay. There you go. Let's draw a little water molecule over here. Alright, so now we have another water molecule over here. Whoopsie daisy. Okay. So we have another water molecule here. It's delta positive of that hydrogen with the delta negative. Now if you look at this scenario, this particular atom, all the hydrogens are happy, oxygen is happy, it's electrically neutral, and its orbitals are full. Okay, so this is hydrogen bonding between water molecule, and this is what gives water many of its amazing properties. So when an oxygen combined to give water, it's a polar covalent bond. Okay. Which means electrons are shared unequally. So there's a slightly delta negative and delta positive, but then they stabilize each other by hugging each other, the negative hugging the positive side, positive hugging the negative side to maintain that electrical neutrality. Now in cartoon fashion, look at how this is what they do. They arrange themselves in a way so that the negative faces the positive, negative faces the positive, like this hydrogen bond. And they can come and go. These are weak bonds, okay? They're not obviously not as strong as Ionic or covalent bond, the hydrogen bond, so they can interchange. So if this one gets pushed off, then another one will come and take its place, etc. Okay. And when the more hydrogen bonds there are in water, the more stable it is. In fact, in ice, it's perfectly geometrical figures like that. Okay. So, the more hydrogen bonds there are in water, the less movement there will be in water molecules, and it would be ice. Okay, so this is so important that please, if I could request to put with me. So this is water molecules H2O, and this is sharing of electrons. And this is the hydrogen bond between two water molecules, between the delta negative oxygen molecule and delta positive hydrogen atom. And that's a hydrogen bond, frequently depicted like this. And this is a three-dimensional representation of a hydrogen bond. In solid water, which is ice, they're beautifully geometrically arranged with maximum number of hydrogen bonds. In liquid water, so, there's fewer hydrogen bonds. That's why it's not as solid. And in gaseous phase, there's no interaction between water molecules. So in ice is actually lighter than water and floats because the geometrical shape allows actually to be greater space between individual water molecules. That's why ice floats. And it is also because of this polarity of water molecules that allows it to dissolve sodium and chloride. Okay, and this is one last thing I'll talk about before I finish here. So if you recall, sodium gives up its electron to chloride, right? And to give an ionic compound. Now, the reason they hang out together is because one is positively charged and one is negatively charged, and to maintain electrical neutrality. Now, if you understand, sodium is a positive charge. It doesn't. The only reason it hangs out with chloride is because it's to maintain this electrical neutrality. It doesn't really care how he gets to do that, to maintain electrical neutrality, right? So this is positive, right? What if you have like a water molecule trying to neutralize that electrical neutrality like this? Let's say you have 3 water molecules here, okay? And positive, so here it is. Ooh, I'm trying to draw this out here. Pretty cool. Positive here, positive here. Okay, now look. So I have a sodium atom. Okay, right here is a sodium atom with a positive charge, right? Now I have an oxygen over here, which is delta negative, okay, and another oxygen that's delta negative, and another oxygen that's delta negative, and the delta negative, right, can neutralize the delta positive charge over there. So the sodium really doesn't need the chloride anymore, right? And the chloride, on the other hand, okay, the chloride does its own thing. So here's chloride, okay, that used to be with the sodium. It can also be neutralized by water. Watch this. Okie dokie. Okay, so okay, there we go. So now we have chloride, which is negative. Now it's going to be neutralized by the delta positive hydrogen ion. So here is delta positive hydrogen atom and a slightly delta positive hydrogen ion between the water, neutralizing the negatively charged chloride ion. So this is the reason why salt dissolves in water, because if you put salt in water, the water will just water molecules will just kind of hug the sodium chloride molecules away from each other, and before long, poof, the sodium chloride, the salt is gone in the water, not visible as is represented here. See the chloride negatively, all the negative charge will be balanced by the positive sides of the water molecule, and then a positive charged sodium ion will be balanced by the negative side of the water molecule, and that's how salts are dissolved in water. I would like to elaborate slightly on the types of bonding to complete this topic next time. Until then, assalamu alaikum.